Hi folks, this is CEO speaking again. Last week we've seen some technologies used in integrated circuits in the logic ones. Today we're going to study in detail the first one. So let's do it. The gate we're going to start today is called the OR gate. As you may remember from the introductory part in the integrated circuits, the logic packages, they contain at least 14 terminals. Now, we're going to establish a kind of pattern when studying the logic circuits. So we're going to do something like that. A, symbol. As you know, all the gates starting with a simple inverter, they contain 4 to 6 transistors or more. So there is no purpose to start drawing such a handkerchief, plenty of transistors around. So for that reason, the whole diagram is considered something like a black box, and the engineers just tell us what that black box does and what is the symbol for it to recognize it. So this, what you see here, is the symbol for the OR gate. I'm going to put it here. So you are going to draw something like this. And you have to know that the inverter is the only package, the only function having only one input. All the other functions, they have 2 inputs or more. So the simplest possible OR gate has 2 inputs. We're going to name the inputs with letters, let's say A and B. And here is going to be the output, like that. Just for you to know, you may have other gates bigger than that. The symbol is going to be the same, but they may have 1, 2, 3 inputs. So if it is the case, you are going to give them letters, something like that, and here is going to be the output. And the same principle applies if you have a bigger gate, like this, having 1, 2, 3, 4 inputs, A, B, C, D, and the output is here. And you may have other similar ones with more than 4 inputs, like 8. For the purpose of simplifying, we're going to start using a simple one with only 2 inputs. But remember, the manufacturers don't make packages only to contain 1 gate inside, because the smallest packages they make have 14 terminals at least. From the 14 terminals, they reserve 1, like this one for the ground, and this one for the power supply, for everything which is inside. So 14 minus 2 is 12. If each of these functions or gate, they contain 1, 2, 3 terminals, 4 gates are fitting perfectly inside. 1, 2, 3, and 4. Today, we're going to only pick up one of them to see how it is operating. So we're going to pick up this one here. Input on the pin 1, another input on the pin 2, and the output on the pin 3. Now, let's go a bit further. B. We've seen the symbol. Now we have to see the mathematical equation. What does it do mathematically? And here is going to be the first tricky thing about that gate. There are more complex gates than this one, but this is one of the trickiest one because it's the first time we're going to introduce something very interesting. So here, the output is going to be A plus B. So what's in the box? We're not interested at this moment what's in the box. If you really want to know, you just go in the specs of the manufacturers and you're going to find out. But I'm going to just use that drawing because it's extremely simple. I'm picking up the 2 inputs and they say, if you add these 2 inputs, you're going to get your output. However, that's a very interesting thing here. That plus here is not the arithmetical addition you know from the pocket calculator. This is called a logic, and I insist on that, logic addition. Logic addition. And what does it mean is a logic addition? Take a look what does it mean. We go for the next step, C, and we're going to draw something called the truth table. The reason it's called the truth table is because if you are able to get that table, you're going to know all the truth about the function. So it's going to be a small table, don't worry about this. Okay, so it's going to be something like this. And the first version we are going to draw is the one for voltages. Here is the input A, on the second column is the input B, and on the third column is the output. So in order to understand and to see what are they doing, we're going to take some measurements. So here, on this white breadboard, I prepared a little trainer for you guys. And according to one of our previous videos, when the light is off, that's equivalent to a 0 logic, or 0 volts. When the light is on, that's equivalent to a 1 logic. But we're going to measure voltages. So at this moment here, the power is on already. How do I know the power is on? Because if I'm watching the multimeter here, and if I measure the pin number 14, I measure 5 volts. So that's how I know my package is energized. And if I measure the pin 7, okay, I measure, the pin 7 here, this is going to be 0 volts. Okay, that's exactly the package. If you can see it, I have an identical one right there. And our OR gate we're going to use today has the code 74LS32. I'm going to come about that later. Okay, exactly that package, I have it over here. So if I measure the pin number 1 is the input A. What do I see on the meter? I see 0.12 volts. It's not exactly 0 volts. It's 0.12. It doesn't matter. I write it here. 0.12. All the values I'm writing here are in volts. Okay? I measure now the input B. The input B is on the pin 2. Is also 0.12 volts. I write it here. 0.12. And I measure now the output. The output is the pin number 3. What is on the pin number 3? 0.16 volt. I don't care about the other decimals. 2 decimals are good enough. 0.16 volt. So far so good? Now, I'm going to change one of these inputs, and you're going to find out later on that combining these 2 inputs together, you cannot have more than 4 combinations. Either both of them are 0, or each of them are 1 in turn, or both of them are 1. So, when I press this button here, as you can see, this LED goes up. That's the, let me see if I did like that, is going to be the input B. So, A is still 0.12 volt. So I write it down because it didn't change. But B isn't. The B is 3.5 volt. 3.5 volt. And the output is pin 3, 3.4 volt. I write it down. 3.4. Next, I'm putting this one off and I make the other one on. And I measure. Pin number 1, input A, 3.5 volt. 3.5. B, 0.12. 0.12. And the output, which is this one, 3.4. 3.4. And the last line is when I press both buttons, as you can see, both inputs are on. So 3.5, 3.5, 3.4. I write them down. 3.5, 3.5, 3.4 volt. You see this? So, at this point, I have the voltages. But what I want to get, actually, is another kind of version of this table, which is about the logic states. The table is going to look identical to the other one. like that. So then, what I'm going to see, this is the input A, this is the input B, and this is the output. I'm going to convert, like a couple of videos ago, with the voltages and logic states. When the voltage of any input is below 0.8 volts, it's a zero logic. So here, I'm going to write only the logic state 0 and 0, and 0 for this one. When any output is below 0.4 volt, and it is, because it's only 0.16, is zero logic. Similarly here, 0. When any input is above 2 volts, is 3.5, is 1 logic. When any output is above 2.4 volt, is 1 logic. Third line, this is a 1 logic, 0 logic, and 1 logic. And last line, 1 logic, 1 logic, and 1 logic. So I converted here the voltages in logic states. Now we can talk about. So now I'm going to write here what is the relationship between the inputs and the output. What do? I just apply the mathematical equation. What the output is? A plus B. So what is 0 plus 0? Is 0. So I write it here. 0 plus 0. And the output is 0. 0 plus 1, 0 plus 1 is 1. Does it make sense? Now, next line, 1 plus 0 is 1. So far, so good. The problem we're going to have, and this is why the function is a bit tricky, is because of the last line. Because take a look what we get here. 1 plus 1 equals, and I'm going to put this in red to be seen, 1. Forget about 2. Because here we go and work with binary, and the binary only has 2 values, 0 and 1. There is no such a thing like 2. So when both inputs are both 1, like you can see here the lights, both inputs are 1, the output is 1. So I'm going to circle this thing, because this is the weird thing about the OR gate. And this is why the addition is not the arithmetical addition, because on your pocket calculator 1 plus 1 is 2. It's called the logic addition. 1 plus 1 is 1. Hey, that's a bit weird. Try to explain to anybody on the street that 1 plus 1 is a 1, and you're going to see what happens. Okay? Now, I have to give you an explanation how this one can ever be true. This is how we draw an electronic diagram. Okay? Here I draw just a battery. The symbol for a battery is a long line, which is a positive. Let's say in our situation is 5 volt. And the shorter one is the negative. So whatever you connect here across these 2 points is the load consuming current or energy from the battery or the power supply. So for instance, if I connect this, I have here a load, okay? And if I connect something else here, I'm gonna call this A, this one B, that's the power supply voltage, okay? And that's the load. And that's the way we draw a diagram. Now, what happens is, in order to understand this one here, we're going to return back somewhere in the middle of the 19th century, when, after inventing the telegraph, the engineers, they realized that they could send the signals and the power for the telegraph along the railroad, along the rails. So somebody thought, and I'm sorry, nobody knows exactly how to identify this guy who did this for the first time. However, somebody was thinking to draw the power supply like that. 2 parallel lines like this, and this is going to be the left power rail, exactly like on the railroad, and this is going to be the right power rail. This is going to be here on the left always the positive of the voltage, and here, if the power is DC, like in our example, the negative of the voltage. So the negative of the voltage is equivalent to that, and the positive of the voltage is equivalent to that. So whatever you draw between these two lines, you form an electric circuit. Let's replicate the circuit doing exactly that function. Here it is. This is my, let's say this is a lamp, or the load, as you wish. And here are the two switches. This is the switch A, and this is the switch B. So here, in this diagram, the purpose for any diagram connected between the positive and the negative of the power supply is that by having some control elements here on the left, to be able to energize the output, because the purpose is to control your load. If it is a lamp, it's just to put the lamp on. So in order to have energy over that lamp here, what do you have to do? You have to put on either the switch A or the switch B. So either A or B has the name of the function. That's exactly the name of the function. The function is OR. So when you ever hear about such a thing like the OR function or the OR gate, what does it actually mean? You have to keep in your mind, because later on when we advance in our projects, and this is why I have some of my playlists about programmable controllers, this kind of thing is so known in programming because these contacts, they are typical ones coming from relays. This kind of diagram is called relay, ladder, if you want, diagram. It's like a ladder because you have the two rails of a ladder, and the steps are everything you draw between the two rails. So, relay ladder. And in the PLCs, this is used for more than 50 years because everybody likes that kind of style of circuits in electricity and power circuits. So then, you put either A or B on. Exactly like here. If none of them is on, both of them are off, like here, there is no energy coming for the load, so the load is off. It's exactly the situation here. Both of them are off, both switches are off, the output is off. If you put A on, if you turn the A on, like this one here, the output goes on, simply because by closing that circuit, you energize the output. If you put only the B on, you also energize the output. But now my question is, if you put both of them on, can you see any bigger power over the output? No, the amount of power is still the same. For instance, if the voltage here is 5, and the power of the bulb, just to take a hypothetical value here, 5 watts, it doesn't matter if you have one switch on or you have both switches on, it's going to absorb 1 amp. 1 amp here, okay? Simply because, as you know very well, the power is voltage times amperage. So 5 volts times 1 amp is 5 watts. It doesn't matter if you have one switch on or two switches on. The difference is if you only have one switch on, if the switch fails, there is no power over the load. If you have two switches, maybe this diagram is a bit more reliable, but it doesn't change the fact that the amount of power going over the load is the same. And the meaning for you, when you see that logic operation called logic addition, which is written on the paper with the same mathematical symbol like the arithmetical addition, 1 plus 1 is 1. In your mind, you have to have two switches in parallel. So I repeat that. The meaning of the OR function or the OR gate when you go in electrical circuits is two switches or two control elements in parallel. That's the meaning of either A or B. So you can have either A or B or both on. It doesn't matter. Then if you have at least one of them on, the energy goes for the output. And this is the actual meaning of all that. Okay? Then I think we can go for D. The D is called the timing chart. It's like a picture. It's like a drawing you are going to see over an oscilloscope. If you had the oscilloscope first, you have 3 channels. On the horizontal line is the time, exactly like on the oscilloscope. And on the vertical line here is the voltage size, voltage. I'm going to have here representing on the first timing chart the input A, on the second timing chart the input B, and the output on the third one. Okay? So I'm going to pick up 2 hypothetical switches here just to see how this thing is working. Supposing I have the switch off and somewhere here it goes on and it stays on. The B, let's suppose it was on, it stays on up to here, it goes off for a while and it goes back on. It's like you play with these switches randomly. Okay? The key to understand how the function performs is that. Very simple rules. First rule is anytime any of the inputs are switching 0 to 1 or 1 to 0, because this is the level, by the way, for the 5 volts, this is the level for 0 volts, this is the level for the 5, for 0, and so on. So here is the first time one input goes on, is this input. Here, the other input changes. And here, this one changes again. So for each such interval of time, from here to here, for instance, the second rule, we write the value. From here to here, what is the value of A? Is a 0 logic, because it's down. From here to here is 0 logic again. From here to here, it went up, so it's a 1 logic. And from here to the end is also 1 logic. Input B. For the same interval of time, from here to here, the input is 1. From here to here, the input is 0. From here to here is 0 again. And from here to the end is 1. So according to our truth table, because the truth table and the timing chart, they have to work for the same integrated circuit for the gate called OR, we look for it. If A is 0 and B is 1, we're right here. A is 0 and B is 1. What is the function? Is 1. I write it down. When both of them are 0, 0 plus 0 is a 0. 1 plus 0 is a 1. Take a look. 1 plus 0 is a 1. And when both of them are 1, the function responds with a 1. Is the last line. So the last thing remaining here, when it is a value 1, I draw a line up because this is the line for 5 volts. When it is 0, I put it down. Here it goes up again. So that's how the output responds when the inputs are moving like that. We're going to see much later that as long as the functions are very simple, the key to understand is the truth table. When the functions become more complicated, the truth tables, they become too long, too cumbersome, so then it's going to be better to use the timing chart. But at this level, just to show you how they operate, we can use either the logic states, the truth table, or the timing chart, and we're going to get the same result because we talk about the same gate. Next point in our pattern here is E, packages. Packages, embedding the OR gate or function. TTL packages. Remember, there are 2 basic technologies, TTL and CMOS. For TTL, we're going to have 7432. Remember, when we discussed the technologies last time, 74 is the meaning of the commercial for TTL, and whatever is the number after that is the schematic. And now we know 32 is the diagram for what? Is the number for the OR gate. It's exactly the number specifying this kind of package when you have 4 gates inside, all of them OR. So the package code is 32. You may also have 74 ls32. Like our package here, this one here, is 74 ls32. And you can also have 74 ALS32. Remember, LS stands for low power, short key, or high speed. ALS, advanced LS. So here I'm going to circle again, and you can see the number remains the same because it doesn't matter the technology, original TTL or LS or ALS, the diagram is still the same inside. TTL. And now CMOS. Remember, in the CMOS, there are 3 versions of that technology: first generation, second, and third. For the first generation, there is a package called CD4071. So the 4000 series, the number 71 specifies OR gates inside. But when it's the second generation, is 74 HC32. Remember, HC, high speed, C is the first letter of the CMOS. And when you see the number 32, is because it has the same pinout as these ones. And there is another one, 74 HCT32. HCT32. So now I can show you the actual layout. You're going to find this, of course, on Google Drive. I'm going to give you the address. So the package here in the top, the one we used, is the same pinout for 7432, 74 LS32, 74 ALS32, 74 HC32, or 74 HCT32. And the 32 everywhere is what? Is the number specifying you have 4 OR gates inside oriented exactly like that. However, when you go for the CMOS, the first generation, CD4071, or the Motorola made, remember Motorola puts a 1 before any code, but if you remove the 1, you get the same 4071. Then, the first gate and this one here, they are oriented exactly the same. The inputs are on the pins 1, 2, and the output on 3. However, this one is not the same. Take a look. They are oriented opposite way. So the CMOS here and the TTL or the HCT, they are not compatible because this gate here and here are not oriented the same as these ones. So be very careful, because if you change, they are still OR gates, but if you change the TTL packages or these packages written here with that one or that one, the gates don't have the same pinouts. Be very careful about that. By the way, how do you find all that? It's very easy. I'm going to stay here for a minute. If you just go and look in your Wikipedia, you can find a list, if you ask for it, the list of the 74 series, and if you just go and go on the list, you're going to find here 74X, where X may be any letters for different technologies, quad to input or gate. And if you click on that, you're going to need the specifications of the manufacturer. This is, remember, SN, the one made by Texas Instruments. I don't want to waste time to go there. If you click and you go asking the same Wikipedia for the CMOS, you have a whole list of the 4000 series, and you just go down, and somewhere you're going to find 4071 quad to input OR gates. And if you click here, you can find either the package made by RCA or from Texas Instruments, okay? Or you can simply Google the function, the package you need, if you have any idea about the package, and you're going to find the PDF file. So now, one thing remaining. We explained a lot of things about the OR gate, how it is working. A, the symbol. B, the mathematical equation. C, the truth table. D, the timing chart. E, packages embedding the OR gate. 1 point remaining, and we're going to respect that kind of pattern for all the functions we're going to study, for all the simple gates. Applications. We studied that function. We know what the OR does. 2 switches in parallel to control the output. But what is a typical application for this kind of gate if you want to use it? So I prepared here a little project for you, which is right here in the top. What's going to be? If I put it on, you're going to see it. It's very easy to get it. Okay. Here you see the pace. And with that pace, the counter is starting counting. And after a while, the circuit is going to reset, going back to 0, and is going to be automatically reset. I'm not touching any button, as you can see. And it's going to be reset for about 10 seconds. I put a buzzer over here and some labels on it to reduce the sound, to muffle the sound because it's very strong, okay, otherwise. And after the 10 seconds reset, now, you see, both digits are showing a 0. The circuit is reset. It's going to restart counting, and now starting the second cycle is going to count only cycles of 35 seconds precisely, okay? So just watch, one cycle, okay? So it's going up to 35 seconds, and the circuit is reset automatically. I'm not doing anything, okay? And then I'm going to explain you when I'm going to use the OR function. The actual package for the OR function is over here. Did you hear it? The package is showing a 0 now, okay? And is reset automatically. But when it's starting counting, as it does now, let's say I want it to count up to 15. Exactly at 15, I'm going to press this button. You see? So this is a manual reset. It is going to last also the 10 seconds we talked before. And now it's restarting counting. So I can apply the reset in 2 ways. Either automatically from the diagram or manual reset made by myself. So this is the meaning of using the OR function. You cannot put the 2 resets together because if they touch each other, take a look, 35 seconds. If you put them together, they're going to interfere with each other. This is why you have to put each reset in the OR gate on one input each, manual reset on one input, automatic reset on another input. So this is my manual reset is going on one input. This is the automatic reset is going on another input. And then the output is going to go here to reset the packages. So here, if I leave it one more time, at exactly 35 seconds, it's going to go up. 34, 35, you see? So at 35 seconds precisely, this circuit is reset. But after the 10 seconds reset, I'm going to leave it only for 5 seconds going on, and I'm going to reset it manually. 1, 2, 3, 4, 5. And I reset it. So this is the use of the function or the gate OR. Either manual reset or automatic reset. That's an example of how can I control it. So for today, we did everything you should notice about the function OR. Next time, because you have to understand where this kind of logic operations are coming, like logic addition, we're going to find some others which are even worse in terms of complexity than the OR gate. Who should you think, who should you thank, or who should you blame for is going to be for the next time. Until then, thanks a lot for watching. See you next time, next Tuesday. Bye-bye.